So this video here deals with function applications. We've spoken in the past, we've talked about how to maximize the volume of an open top box. We had the infamous gutter problem, just different maximizing problems. Well, now we're talking about compositions of functions, and we're going to formally talk about how to apply compositions to function applications. So on the back of year one review sheet, there were a couple word problems that we did not get around to doing. The one dealt with a baseball diamond with 90-foot sides. So if this is home plate right here, and this is first base and second base and third base, and you know what? I need a new home plate here. That's just not going to cut it for me. So home plate is a pentagon. It's got 5 sides. So there we go. There are 5 sides there. The distance we mentioned was 90 feet away. And you're told that a runner has a 9-foot lead. So there's a person standing right here, a 9-foot lead off of, we'll call this first base. And this is second, third, and home. So this runner has a 9-foot lead. He's 9 feet away from first base. Okay, so if we wanted to find the straight line distance from home to the runner, that'd be Pythagorean theorem. We'd say 90 squared plus 9 squared equals the distance squared. We would then take the square root of each side. Okay, well, we're also given information that the runner is advancing. The runner is running towards second at a rate of 27 feet per second. So with a little bit of math, you know he has 81 feet to go, 27 feet per second, 81 over 27. It'll take him 3 seconds. That's important when we talk about our domain later. It'll take him 3 seconds to reach second base. Well, we are charged with the task of finding the straight line distance. The straight line distance from home to the runner at any time t. Which means I don't know if time is 1 second, 2 seconds, 1.4, 2.7. It's t. Okay, I need to find what is the distance from here, where the catcher is, to where the runner happens to be. I don't know if no time's gone by and he's here, or 1 second's gone and he's here, and 2 seconds he's here, 3 seconds he's here. I don't know that. I want to find the distance he is at any and all times. Okay, so we're going to draw that triangle. There's my hypotenuse. Here's the 2 legs. Now this one leg we know is always 90 feet. Now this differs with time. At no seconds, he's only 9 feet away. But after 1 second, he's 9 plus 27. After 2 seconds, he's 9 plus, that'd be 54, 63 feet away. So at any given time, he's 9 plus 27t. Which means if I want to solve for d, I can do the Pythagorean theorem and say 90 squared plus 9 plus 27t squared is equal to distance squared. Distance would then be the square root of 8100 plus 9 plus 27t quantity squared. And that is my distance in terms of time. So we can find at any time t where this runner is located. Now we were not asked to find any specific distances or anything, but if we wanted to maximize or minimize this, we could graph this. We would know that our domain, which is a set of t values, would have to be between 0 and 3. Right? You can write an interval notation or inequality notation or whatever notation you really wanted. Okay, so our domain would be between 0 and 3 because at 0 seconds, nothing's happened. At 3 seconds, he's standing on the base. A second, he's safe. All right, so that would be our domain for this problem. Now let's quickly look at the next problem that was on that sheet. The next problem dealt with a cylindrical tank. So let's draw a cylinder here. Cylinders are kind of easy to draw. Draw two vertical lines, a circle at the bottom, half solid, half dotted, and a circle at the top, completely solid because it's all visible. We're told that the diameter of this tank is 4 feet. Now the important part of that is that the diameter really tells us the radius. Okay, and we're talking about a cylinder. We know that the volume is pi r squared h. We're also told in the problem that the volume changes at a rate of 10 cubic feet per second. 10 cubic feet per second. Now this is the rate at which the volume changes. I have it labeled V. In calculus you'll get notation called dV dt. It's the rate of change. We're not real familiar with that yet, and that's not a problem at all. Just know that 10 cubic feet per second is the rate volume is changing. After 1 second, it's got 10 cubic feet. After 2 seconds, it's 20. After 3 seconds, it's 30 cubic feet. So the volume itself is actually changing just like the runner's distance was. So volume is equal to 10t. So 10t has to equal pi times the radius, which is 2, squared times the height. And we are charged in this problem with the task of finding out what the height or the depth of the water in the tank is as a function of time. So right here, height is dependent upon volume and radius. Well, the radius doesn't change, but volume is dependent upon time. So we took our volume equation, we plugged it in, and we can now solve for height in terms of time. And I can simplify that since both those numbers are even. And I can say that my height is 5 times time divided by the quantity of 2 pi. And we have now put height in terms of t. Height is a function of time as opposed to volume being a function of radius and height. And that was our mini lesson for today.